So, thank you. I'm Ian Fox, here to talk today about contextual motifs. So, we're sort of at the end of this time series analysis block, and you've probably heard this picture a couple of times by now, but I'll give it one more time just to hammer it home. We are seeing an increasing number of wearable monitors being deployed right now, especially for medical data. Now, this is great. Wearable health monitors mean that we collect more time series data, and there's good evidence that this additional time series data can be used to improve patient outcomes by enhancing treatment strategies or issue detection. As a particular example that I'll use throughout this talk, I'm going to talk about continuous glucose monitors for measuring blood sugar of individuals with diabetes. Now, historical measures of testing blood glucose levels are basically manual monitoring. You'll take a reading of your blood sugar once before meals, once after meals, maybe before bed. This results in a sparsely sampled signal, and it can be sort of difficult to interpret. Recently, there have been sort of new mechanisms called continuous glucose monitors, which automatically and passively measure blood glucose values throughout the course of the entire day. This results in a much higher dimensional signal, much more evenly sampled, and you can see some interesting patterns that you might miss with the sparse sampling. So, for example, we see an increasing trend of blood glucose towards the end of the day that you'd miss with manual measurement. This is all good. However, increasing amounts of data can be difficult for patients or physicians to interpret, and in order to extract actionable insights, can require a little bit of additional analysis. This motivates us to look for a low-dimensional representation that maintains the sort of fine temporal granularity that we see with the raw representation, because we don't want to miss out those extra new fancy insights. This all goes to present the idea of motifs. Now, motifs for time series analysis, they're very well studied, they're pretty broadly used. A motif is a subsequence of a signal that occurs more often than you might expect. It has great support over some database of signals. Here we just have an example of a signal, and the highlighted section might be a motif in that signal. It's a pattern that we see. So this is all, quite good, but there's been some evidence that vanilla motif representations can lack discriminative power with physiological signal applications. And this might happen for a variety of reasons. And so our goal is to try to improve the discriminative ability of this motif representation while maintaining its sort of low-dimensional interpretability, which is its main asset. Here we just have a little example of a motif discovery pipeline and how you might use it for a learning problem. We start off with our signal or a database of signals. We discover the recurring subsequences within those signals. We extract some sort of feature representation here, just the count of those different types of subsequences, and we use that as an input to a learning algorithm. Now, we're not the first people to think of trying to enhance motif representations. Previous work has looked at adding supervision to the motif discovery process to discover more discriminative subsequences. However, our approach is interested in an unsupervised method. Additionally, there's been research looking at sort of motif co-localization information or broader structure in motif patterns. Our work differs from that a bit in that we are interested in jointly discovering motifs and these broader patterns. This past work looked at those as sort of two separate steps in the pipeline. So our overall hypothesis is that adding contextual information to our motif representation will improve their discriminative performance across a range of tasks for physiological signals. Now, okay, so we've sort of been talking a little vaguely about adding in contextual information. What is context, right? I mean, it's something which is very domain dependent, which can have a lot of definitions. The main one that we're going to be using is that context are transient external phenomena which affect the meaning and interpretation of the signal. So sticking with our glucose example, here we have an example of 2 different days of continuous glucose data that undergo 3 basic contexts. The first is a fasting state, so the individual has not consumed any food recently. We might have a small meal context, so they've had some small amount of food in some past X hours, and a large meal context. And we can see that these contexts are transient. They don't last particularly long within the signal, and that they are also external and externally generated. So they have a sort of separate generative process than the process which generates our signal observations, which means that we can do things like have different orderings of contexts throughout different signals, or we can even have completely different contexts occurring in different signals. How do we incorporate this idea of context into our motifs? Well, the answer, as the name of the talk might have implied, is contextual motifs. So contextual motifs are very simple. They are the motifs that occur in the signal. Here we have our motif representation. We've got two different types of motifs outlined. It might be a little hard to see, especially over in the corners, but we have basically two instances of spike motifs and two instances of little jag motifs. The contextual motifs take into account the context under which those motifs occur. So instead of having two underlying motifs in this contextual motif representation, we still have the two underlying motifs, the two little spikes, the two jags, but we have four contextual motifs because we have the actual underlying motifs, and then whether or not they occur under the plain context or here the shaded context. So there we have it. There's contextual motifs. I guess it's time for lunch. Well, no, obviously not. If it was that simple, then I wouldn't be here to sort of talk to you about this. The main issue is that up to right now, when we've been talking about context and contextual motifs, we've been imagining the signal like this, where we have our signal and the different explicitly labeled context regions. But as people who work with basically any form of time series data know, we often don't have data that looks like this. We have data that looks like this. That is, we do not have explicit labels for the context that we're interested in reasoning about. Okay, so now we need to think about how do we discover contextual motifs in the absence of context. And there are two main approaches that we examined for doing this. There's two-stage inference, which sort of follows from previous work, where we are interested in separately inferring the context and the motifs. And we talk about that a lot in our paper. You can check it out if you're interested. What we'll be focusing on for this talk is joint inference, that is simultaneously inferring context and motifs, or the repeated subsequences throughout the signal. Now, in order to do this joint inference, we're going to need to take a step back from our previously sort of intuitive notion of context as, meals or no meals, and go into something a little bit more abstract. To sort of get us ready for that and get us ready to understand contextual motifs in a joint inference approach, we're going to talk about a baseline approach, a motif mixture model. So this sort of follows from standard practices in motif discovery with genetic data, where we essentially view signals as compositions of different motifs. And this is essentially in the genetic literature, what you have is you have a mixture of multinomial distributions. Since we're interested in time series data, not categorical, we are looking at a mixture of Gaussian distributions. So this is essentially just a Gaussian mixture model. One important thing to note is that the dimensionality of the Gaussian distributions which we're drawing from is equal to the motif length. That is, a motif is one draw from this high-dimensional distribution. And so we have a little bit of notation here. We have our motif mixing parameter. We have the motif indicator, this Zj. We have the motif parameters, which are sort of indexed by these motif indicators, and then we have our actual signal that we're observing. To extend that to a contextual motif mixture model, we're adding in this extra contextual layer, which adds some broader structure to the signal that we generate from. So here, the main differences from the motif mixture model to the contextual motif mixture model is we've added in this contextual window layer, where before we go and draw any motifs, we first draw the context, and this context determines the motif distribution. So just walking through the generative process here, for each of our categorical windows, we choose a context, and then there's going to be multiple motifs occurring within each context window. For those, we just choose our motif label, or we choose the sort of motif cluster that we draw from, and then we observe the actual motif. There we go. In order to do inference on this model, to discover the contextual motifs, the sort of ultimate things that we're interested in are these categorical motif labels and the categorical context labels. However, to find those, our sort of exact inference thing would involve maximizing this term, and as you can probably imagine, as with any sort of non-trivial graphical model exact inference isn't exactly tractable, so we're using an approximate inference approach using MC-MC sampling implemented with PyMC3. For more details, you can look in the paper on that. So there we go. We have a contextual motif mixture model. We've presented a method to jointly discover context and motifs. How does that go to our original idea? How are we going to show that this is a better representation method? Ultimately, for our interest, a better representation needs to have better discriminative capacity. So in order to look at that, we're going to look at our glucose data and examine the predictive ability of these motif and contextual motif representations across a variety of tasks. Remember, because our approach is unsupervised, for each task we're using the same representation. Basically, there's only one instance of having to actually learn the motifs and contextual motifs. The 4 tasks that we're interested in break down across 2 different prediction types and 2 different prediction ranges. The 2 types of prediction are hypoglycemic and hyperglycemic prediction. So these are just instances of low or high blood sugar, and they're sort of bad for a variety of reasons, and we want to avoid them, and to avoid them, it helps to be able to predict them. And we're also interested in predicting over 2 windows of time, a short window of time where we use a day of data to predict is there going to be a hypo or hyperglycemic event in the next hour, and a longer term prediction where we say, oh, is there going to be a hypo or hyperglycemic event over the course of the entire next day? One thing that I should note now is that the inputs to our sort of learning model can vary depending on the type of motif discovery that we're using. Remember, from the motif mixture model, we discover these motifs. We can use that as input to our model. From the contextual motif mixture model, we get out both these motif labels and the context labels. And we can use either the motifs, just the context, or both of them together as inputs to our model. The data that we're using in order to sort of do all this evaluation is a fairly sizable collection of continuous glucose monitoring data, 32,000 hours, from 40 different patients with type 1 diabetes, collected under a range of normal living conditions. And here I just have outlined a few examples of what hyperglycemic events look like and what hypoglycemic events look like. Those are the things that we're trying to predict. Time to see some actual numbers. So we're presenting, again, we got our sort of 4 different tasks and our 2 different methods. So to break things down first, let's just look at the hypoglycemic results, where we see the short-term and long-term task for the motif mixture model. They're pretty different. The short-term task is much easier in this formulation than the long-term prediction task, which is maybe not too surprising, right? It's easier to predict things that are going to be happening soon versus things that are happening over some long range of future time. Looking at the difference between hypoglycemic and hyperglycemic prediction, we see some variance in the difficulty of those tasks as well, where it appears to be easier to predict hyperglycemic events. Now, for the contextual motif mixture model, here what I'm showing are just the results of the motif discovered, not the contextual motifs. So going back here, just this little box there. But we see that the motifs discovered by the contextual motif mixture models has a consistent, if modest, improvement over the contextless motifs discovered by the baseline approach. So that's really nice. But what about the contextual motifs? Well, it turns out that with the real data, there's the context which we discover is a little bit too noisy to observe a similar increase in performance. To sort of get a sense for how well our context inference approach is working, we turn to simulated data, where you can basically generate as much data as you please, which is always nice for learning, and we can also vary the effectiveness, the sort of inherent effectiveness that the contextual motifs should have on our outcome. That's this beta 1 parameter down on the x-axis. So we look at 3 basic representations. Might be a little hard to see, it's a little faint. But that orange line is just the motifs discovered by our contextual motif mixture model. So we see that as the contextual motif importance improves, the vanilla motifs also improve in terms of their predictive performance, which makes sense, right? Our notion of what context is different distributions of motif frequency, which you would expect to be able to discover to some capacity just by looking at sheer motif counts over the course of the signal. When we add in a 2-stage inferred context, where we basically take our vanilla motifs and then we say, oh, well, let's try to figure out what the context was retroactively, We see a modest improvement in performance, so that's encouraging. It does help to consider context. And when we consider jointly discovering, we use the context that we sort of jointly discovered with our motifs, we see a big boost in performance, which is pretty encouraging. It really goes to demonstrate that context can sort of help discover motifs, and motifs can help discover context. So this demonstrates that our contextual motif representation can be more discriminative than a vanilla motif representation. But we also still had this idea of interpretability, right? We want to make sure that we're maintaining the interpretability of the motif representation. So here are some of the motifs discovered by our contextual motif mixture model on the real glucose data. And we see a pretty interesting variation in sort of structural patterns. You see, there's sharp increases, we see some decreases, we see a spike, and we even see a jag, sort of like we illustrated earlier. So we're seeing some interesting structural variation in the patterns which we're discovering over our data. Looking at the context, we've decided to try to figure out what were the motifs that are most indicative of each context, indicative here in terms of sort of difference in relative probabilities of occurring under one context versus the other. And we see a pretty interesting observation that here we're discovering across two different contexts. The red lines are the most indicative things from one context, blue from the other. And we see there's this big difference in the variation of the motifs. Basically, the motifs in the red context have a much wider range than those in the blue context. And that's fascinating because going back to our original sort of intuitive idea of what might be a reasonable context for glucose data, it was meals or no meals. And it turns out that from a physiological standpoint, one of the best indicators that you are in a sort of state where you've just recently eaten is the variability of your glucose signal. So it appears that our context is sort of natively capturing this idea of variations in glucose values. So, in summation, we've introduced a framework for talking about adding context to motifs, contextual motifs. We've presented methods to jointly infer motifs and the context under which they occur. We've demonstrated that the motifs discovered this way can be more discriminative than motifs discovered using a sort of vanilla process. And we've demonstrated the efficacy of contextual motifs in simulated data. So thank you for your time, and I'll take any questions if you don't want to rush to lunch.